Today we have graph by finding domains, the domain intercepts, asymptotes, the increasing slash decreasing interval, the local min or max, concavity, and inflection points. So this question is basically asking us to graph the function f of x. So we have f of x is equal to x squared plus 7x plus 13 all over x plus 2. So let's go ahead and first start off by finding the domain. Remember, the domain is basically where the function is undefined. To find a domain, we set the denominator equal to 0, and that will give us a value of -2. So if you plug in -2 into the function, that will be undefined. So this means that the domain is x such that x cannot equal to -2, because we cannot plug in -2 in there and get out a value because it's undefined. So we can also write the domain as -infinity to -2 union -2 all the way to positive infinity. So that's how we can do the domain for this function. So now that we have the domain of the function, what else is it asking for? It's asking for the intercepts. So let's go ahead and find those. So let's go ahead and find the intercepts. And how would we find the intercepts? Let's go ahead and find the y-intercept first. So we're going to have to set the function, the whole function, equal to 0 to find the y-intercept. So let's do this right now. We have f of 0 is equal to 0 squared plus 7 times 0 plus 13 all over 0 plus 2. This will give us 13 divided by 2, which this equals 6.5 if you divide. So that is going to be your y-intercept. So we already have the y-intercept. So let's see, y-intercept already here. Y-intercept is basically 6.5. That's going to be your y-intercept. Your y-intercept is 13 divided by 2, aka 6.5, I believe. Let's make sure. Let's see, we have 13 divided by 2, 6.5, yeah. So 6.5. It's your y-intercept. There we go. Okay, so let's go ahead and find out the x-intercept. So in order to find out the x-intercept, let's go ahead and basically let's go ahead and factor this. So we have x squared plus 7x plus 13, and we see here that we can't really factor this, so let's go ahead and use the quadratic formula to find our x-intercept. So the quadratic formula is x equals to -b plus or minus the square root of b squared minus 4ac all divided by 2a. So now let's move up here and do the this. Actually, no, let's keep it down here. All right, so let's go ahead and plug in our values. So -b is going to be a -7 plus or minus the square root of let's see, square root of 7 squared, which is 49, minus 4 times a. What's a? A is 1. C is 13 all over 2a. 2 is 2. That is 2a is 2. So let's go ahead and solve this. Oh, and just a note I forgot to mention, whenever we have a function like this, like a rational one, and we want to find where this is equal to 0, the fastest way to do this is just setting the whole numerator equal to 0, because if the numerator is equal to 0, when we divide, we're going to get 0. So let's set this is why I'm setting the numerator alone equal to 0 to find our x, what do you call it, our x-intercepts. So let's go ahead and do this. So in this case, we're going to have an asymptote, by the way, since it's undefined at -2. So we're going to get an asymptote there. So that can't be an x-intercept. All right, so let's go ahead and continue this. This is equal to -7 plus or minus the square root of, you put that into your calculator, you're going to get the square root of -3 over 2. But you see here that we have the square root of -3, something that we can't really have on the real coordinate plane. So this is equal to -7 plus or minus, let's factor out a square root of -1 from the -3, which just leaves us to a -3. I mean, a -3, a +3 divided by 2. And this equals, it's right here. This equals -7 plus or minus I times the square root of 3 divided by 2. We cannot have that in that's not a real root in our coordinate plane, so this basically implies that it has no x-intercepts. So no x-intercepts. So yeah, this is a complex number. We cannot have a complex number in our real coordinate plane, so no x-intercepts. Alright, now that we found our intercepts, let's go ahead and let's see, what else do we have to do? We have to find the asymptotes. Now that we found all of our intercepts, let's find the asymptotes. This is my black pen. Asymptotes. Let's find them. All right, so let's see. Let us find first our vertical asymptote. So like we established that the -2 is going to make this function an undefined, right? So that means we cannot plug in a -2. That means -2 is off limits, so that is an asymptote. That is going to be, since x equals 2, that is going to correlate to your vertical asymptote. So it's like this. You'll see it when we draw the graph. It's going to go vertically. So our vertical asymptote, blue, vertical asymptote is equal to -2. How we established -2. That's your vertical asymptote. And remember, we got that from basically where is the function undefined. So that is your vertical asymptote. Let's go ahead and find let's see. So we see that we have x2, x squared plus 7x plus 13 divided by 2, divided by x plus 2. So let us see. So let us look at the degrees of the function. Basically, the degree of the numerator is greater than the degree of the denominator. So that means we are not going to have a horizontal asymptote. We are going to have an oblique one. So it's going to go something like that, right? That's an oblique. It's not going to be horizontal. It's going to be oblique, like that. So let's go ahead and find our oblique asymptote. And we can do this by basically dividing the numerator by the denominator. So let's go ahead and do some polynomial division. So we have x squared plus 7x plus 13 divided by x plus 2. All right, so let's go ahead and do the division. So basically, what here is going to give me x squared? That's going to be an x. X times x is x squared, and then x times 2 is 2x. And let's subtract. You will get, if this was a negative, by the way, when you subtract, you're going to switch the sign to a positive, by the way. But that's if it's a negative. When it's not a negative, just subtract it normally. So this is going to be 0. 7x minus 2, that's going to be 5x. And then we have, we bring down 13, positive 13. And yeah, what will basically give us 5x here? That will be a positive 5, right? 5 times x, that's 5x. 5 times 2, that's 10. Yeah, I forgot that. So now we are going to subtract. This turns into a negative, by the way. That turns into a negative. So that is going to give us just 3, positive 3. So now we are going to write this as x plus 5 with 3 on the plus 3 on the top divided by x plus 2. So that's how we write basically what the answer that we get here. X plus 5, remainder 3 divided by x plus 2. Yeah, there's a plus sign, by the way, so make sure you write that plus sign. So basically just remember, if the degree of the numerator is basically greater than the degree of the denominator, just do the division and you're going to get your oblique asymptote. So this is going to be your oblique asymptote, by the way, x plus 5. So your oblique asymptote, let's write it here, oblique asymptote. Oblique asymptote is going to be y equals x plus 5. Y equals x plus 5. We got that from the division, so we found it. So that's what we got so far. Let's go ahead and move on to the increasing slash decreasing intervals. So let's go ahead and put it here. Increase slash decrease. So let's go ahead and find that. So let's go ahead and let's see. Basically, to find the increasing slash decreasing intervals, we are going to have to take the derivative, the first derivative of the function f of x. So let's go ahead and take the first derivative of the function f of x and set it equal to 0 to find the increasing slash decreasing interval. So f of x, derivative of f of x. If you know how to take a derivative already, you don't have to watch this part. But for those who need a refresher on taking derivatives, you can. So I'm just gonna take the derivative. Just skip if you don't want to see this part, if you already know how to take a derivative. So but if you want to see, just stick around. So we have basically we're gonna use a quotient rule. I'm not gonna write out the whole quotient rule, so this is just a review on derivatives, a tiny review on derivatives. So we're gonna have g of x. Let's say this is our f of x and this is our g of x. So let's go ahead and this is our g of x, by the way. So the quotient rule states that g of x, which is x plus 2, times the derivative of f of x, which we're going to use the power rule. Basically bring down 2 to right here, subtract the 2. So you're going to get the derivative of 2 of x squared is just 2x. The derivative of 7x is just 7. So let's go ahead and do that. I'm not going to go too much into detail on the power rule, but let's just go ahead and do that. We have 2x plus 7. That's a derivative of f of x, our top function. So minus let's see, minus f of x, which is we establish as x squared plus 7x plus 13 times the derivative of g of x, which is just 1. You divide it by g of x squared. G of x is x plus 2 squared. That's a squared, by the way. So that's going to be your derivative. Now let's go ahead and do the algebra and simplify this thing. So this is going to be equal to basically just multiply across. Like do your foiling or your box method or whatever to multiply this. This you could already multiply it and then subtract both of them. And we're going to get our derivative. So when we FOIL it out, slash doing the box method, we get 2x squared. These two, by the way, when we both multiply these, 2x squared plus 11x plus 14, and then we divide. We minus. Remember, you have to distribute the negative sign, so you're going to distribute it to the x squared, you're going to distribute this to the 7x, you're going to distribute this to the 13. So this is negative x squared minus, remember, distribute the negative 7x minus 13 all over g of x squared, which is x plus 2 squared. So now let's do some further simplification of like basically canceling out the like terms. So let's go ahead and do that right now. So basically when you cancel out like terms, we're gonna end up with the derivative of f of x, f prime of x, is equal to let's see, x squared plus 4x plus 1 all over x plus 2 to the raised to the second power. So that's your derivative f prime of x equals x squared plus 4x plus 1. Yeah, that. And now let's go ahead and set this equal to 0. So set that equal to 0 and just basically solve for it. First, let's solve for the numerator. And set the numerator equal to 0 and basically find out what the numerator is. So let's go ahead and find out our numerator, which is, let's go ahead and use a quadratic formula for this. So all right, remember the quadratic formula right here. I'm not going to rewrite it, but let's go ahead and use a quadratic formula, so that when we use a quadratic formula, it's x equals negative b, which is, what is our negative b, which is negative 4 plus or minus the square root of 16. 4 squared is 16 minus 4. A is 1, B, C is 1, so just 1 all over 2. So let's go ahead and do this thing. So we're left with that's an equal sign, by the way. We're left with negative 4 plus or minus 2 times the square root of 3. Once you plug this thing into your calculator, all divided by 2. So you can use some cancellation here to cancel out these 2's. And negative 4 is just going to be negative 2. So we're left with x equals to negative 2 plus or minus the square root of 3. Which, for graphing purposes, let's go ahead and estimate this. You can go ahead and just throw this thing into your calculator to estimate some values of it to make it easier to graph on the number line in our graph. That's x, by the way. X is equal to approximately negative 0.26 and then negative 3.7. Negative 0. Yeah, roughly. This is a rough approximation. It doesn't have to be perfect, but just rough. So negative 0.26, and then another x value of negative 3.7. So that's what you get when you plug this into your calculator. Negative 2 plus or minus the square root of 3. All right, so let's go ahead and where is this function undefined? This function is undefined at negative 2, right? Because if we plug in negative 2 here, that's going to equal to 0. We cannot divide by 0 because that's going to be undefined. So undefined at negative 2. Undefined at negative 2. Now let's go ahead and basically find out where this function, this derivative, this derivative is increasing and decreasing, or this function is increasing slash decreasing. So let's draw our number line. And let's put in our points. We have an asymptote of negative 2. This is our asymptote. So let's go ahead and put that in there. We have our x value of negative 3.7. We have our another x value of negative 0.26. So we need to find out where this function is increasing slash decreasing. So when we plug some values here into the derivative, if the derivative is greater than 0, so basically a positive derivative, we're gonna have an increment in the function. If the derivative is less than 0, so a negative value for the derivative, then our function is gonna be decreasing. So let's go ahead and do that. Basically, just pick any number in between these this number line to estimate the not estimate, but basically just see if your answer is negative or positive. So let's go ahead and do that. Let's go ahead and plug in let's go ahead and go here first. What is less than negative 3.7? A number all the way over here. It's going to be negative 4. So let's go ahead and plug in negative 4 into our function. So if we do that, if we plug in negative 4 into the function, I'm not going to do it, but because I'm going to guess you guys know how to do this already, but if we plug in negative 4 into the function, that's going to give us basically a negative value back. So, I mean, not a negative value. That's going to give us a positive value back. That's going to give us 1 over 4. So that's positive, right? So we're going to write down a positive sign here. So for the sake of time, again, I'm not going to plug in these values. But if we plug in any value in between these two points, let's plug in a negative 3. That's going to give us basically a negative value. So we're going to put in a negative here. Now let's see, any value between negative 2 and negative 0.26, just pick anything, plug it into the function, into our derivative function, and that is going to be a negative value. Any value basically greater than negative 0.26, so you can put in basically anything you want that's greater than this value, is going to yield a positive value. So just for the sake of time, I'm not doing that. So let's go ahead and find out where this is increasing slash decreasing, and we're going to find our local min and local max already in this thing, in this portion of the question. So it's increasing at, just increasing at, let's see, the derivative is positive here and there, right? So it's increasing at negative infinity all the way to negative 3.7. Negative infinity all the way to negative 3.7. Where else is it increasing? Negative 0.26 all the way to positive infinity. Negative 0.26 all the way to positive infinity. That's where it's increasing. Now let's go ahead and find out where it's decreasing. Where is it decreasing? Where the derivative is negative. So it's decreasing from negative 3.7 all the way to our asymptote of negative 2. Negative 3.7 all the way to our asymptote of negative 2. Remember, that's where the function is undefined. And it is decreasing again at our asymptote of negative 2 all the way to negative 0.26. Negative 2 all the way to negative 0.26. So that is where our function is increasing slash decreasing. Let's go ahead and box our answer. That looks messy, but whatever. That's where it's increasing slash decreasing. So, oops. Let's go ahead and find the local min and max. So in order to find, let's write it in black. Let's local min, let's write it here. Local minimum, max. Let's do the max first. And then local min. All right. So let's go on to our number line here. We see that the value here is positive, so it's growing. And then it hits negative, so it's decreasing. It's like that, right? On top of the little parabola, since it's on top and all this is increasing and decreasing, there's a top here. That is a local maximum. So at the point negative 3.7, it's going to be our local maximum. So our local maximum is Our x value is negative 3.7. So what we want to do is we want to plug in negative 3.7 into our original function. So let's go ahead and plug in negative 3.7 into our original function, not the derivative, but the original function. And let's see what kind of value we get. And if we do the math, again, I'm not going to show it for the sake of time, but if we do the math, we're going to get, if we do all the evaluation stuff, we are going to get negative 0.46, around negative 0.46. So negative 0.46, that is going to be your local maximum. Now let's find our local minimum. This basically cannot be a local minimum. It's an asymptote. So let's go here. It's negative going down, positive going back up. This parabola has a minimum, has a bottom, right? So negative to positive. This parabola has a minimum. So our minimum is negative 0.26. Again, plug this x value into your original function, and we should be getting a 6.46. 6.46. So that is your local maximum and your local minimum. So we already found those. So we already found our local maximum and our local minimum. Let us go ahead and move on with the question. What is it asking? So now that we already found this, so let's find finally the concavity and inflection points, and then we're gonna be able to, what do you call it? We're gonna be able to sketch the graph, sketch the curve. So let us go ahead and find the concavity. It's gonna be a long problem. Let's go ahead and find the concavity. The concavity and inflection points. Oops. Concavity and the inflection points. Let's go ahead and find that. So we're gonna have to find the second derivative of the function. So I already basically did a review on finding a derivative using the quotient rule. So for the sake of time, I'm just gonna give you the second derivative. So the second derivative of the function is basically f double prime of x. F double prime of x is equal to 6 divided by x plus 2 to a third power. So that's the derivative, the second derivative of our function if we were to compute it. Just to let you know, if you didn't know, you can compute the second derivative by doing this whole process all over again, but this time with this function instead of the first function. So just that, you know, it's not important to show you since it's the same process. So let's go ahead and find the concavity. So when we find the concavity, we basically set the second derivative equal to 0. And then we solve for at least, try to solve. We see that basically there's pretty much no solution. When we multiply by both sides, we're going to get 0. This will cancel out. And 6 does not equal 0, right? So there is no solution. So no solution, right? No. Oops, not that one. No solution. That means we get to use our asymptote. Use your vertical asymptote of -2, because that's where pretty much that's where the function is undefined. So let's go ahead and use our our basically vertical asymptote. Again, let's draw our number line. We have a -2 here. Again, all you have to do is just plug in values that is basically less than -2 and then greater than -2. So let's go ahead and plug in our values. You know, let's choose, for example, let's choose f of -3. I'm not going to show the math, but if you put in f of -3 into the function, you are going to get a -6 back. So you should be able to get a -6 back if you plug in a -3 here. -6. So that means that we're going to have a negative value here. a negative second derivative value. And if the second derivative is basically negative, that means it's going to be concaved downwards. Not upwards, but downwards. You'll see what I mean once we do the graph. So let's plug in a -1, because -1 is basically greater than -2. If we plug in a -1 into our function, we will get a +6. So let's go ahead and write the plus sign for positive. So basically we have concavity at, we have concave up. It's concaving up, right? It's going like this, not like that, but like this. Concave up. It's going up at it's going up at -2 all the way to positive infinity, because that is where the second derivative is positive. So -2 all the way to positive infinity. That's where it's going up, concaving up. Now let's go ahead and see where it's concaving down. Concave down. Where is it concaving down? Where it's negative, right? So it's all the way negative infinity all the way to -2. Negative infinity all the way to -2. And that is where our function is basically the concavity of our function. So that is how we figure this out. Just plug in any number that's kind of like, you know, where you want to find in the number line. Again, we plugged in a -3 to get a -6 value. We plugged in a -1 to get a +6 value. So let's go ahead and now we can find our inflection points. Let's find our inflection points. Just plug this thing into the original function, but remember that that is not where it's that is where it's undefined. So we plug in a -2 into the original function, you're gonna get an undefined answer thing back. So that we don't have a inflection points. So no inflection points. NA not available. No inflection points. So these are our inflection points. So we have none of them. Inflection points is basically where the function changes concavity. So where it changes from up to down and whatever. All right, now we can go ahead and finally graph our function. We can sketch it. So let's go ahead and do that right now. So now I just drew a Cartesian plane. We are going to basically sketch our curve finally using the information we have calculated from basically all of what this was asking for. So we're gonna go ahead and basically graph it at this point. So let's go ahead and find these increase by 1, by the way. So let's go ahead and find our let's graph our asymptotes first. So if you remember, we established our asymptotes to be the vertical one, -2, and the oblique x plus 5. So the vertical one is just going to be a -2, and we're going to draw a straight line. I'm going to go ahead and draw this in blue. So I'll be right back. I'm going to go ahead and draw the vertical asymptote of x equals basically -2, so that's where it's undefined. So let's go ahead and draw that right now. It's basically just a vertical line right here. So this is what your asymptote is supposed to look like. This is where the function is undefined. It is basically at -2, vertical because it goes up. So let's go ahead and find our oblique asymptote now. So since we did the whole dividing thing, the whole polynomial division thing, we found that there is an oblique asymptote from this, which is at y equals x plus 5. So that's basically just a straight line. Well, you know, a straight line, but oblique. So basically we're gonna find, it's just a line. And let's go ahead and basically plug in some values. So let's plug in a -3 in there. So -3 plus 5, that is +2, right? -3 plus 5 is +2. So let's go ahead and plot some points for our line. So -3, we established -3 plus 5 is +2. So -3 all the way to +2, it's somewhere around here. Kinda. So -3 plus 5 is +2. Let's plot another point in there. asymptote in this equation, function, whatever you want to call it. So let's plug it in. So let's plug in 3. 3 plus 5. What is that? That's 8, right? So let's go ahead and go to 3. 3 plus 5 is 8. 1, 2, 3, 4, 5, 6, 7, 8. And then 3. 3 plus 5 is 8. So 3, 5, 3, 8. So this is going to be a little challenging. Somewhere around there. Somewhere around. Oops. Okay, somewhere around here. And then, I don't know, I'm just making sure at this point. Yeah, somewhere around there. So just connect these two dots with, again, our blue dotted line. That's going to be your other asymptote. So I'm just going to go ahead and connect these two dots, and I'll be right back. All right, so yeah, so this is how we did the oblique asymptote. This line, let's go ahead and label it as this line is, just go ahead and label it as x equals -2. This line, let's label it as y equals, let's go down here, y equals x minus 5, right? That was our x plus 5, sorry, x plus 5. So that is your those are your equations for the lines, our asymptote, our vertical, and our oblique. There's no horizontal here, so let's go ahead and do some more plotting. Where's my red pen? Hold on a second. All right, let's go ahead and do some more plotting. Let's plot. Let's go ahead and plot our what do you call these? Our intercepts now. So basically the function crosses the x or y axis. So no x-intercept, so we don't have to worry about that. Our y-intercept, which is 6.5. Let's go to the y and plot 6.5 in black. So let's go to our y and plot 6.5. So 1, 2, 3, 4, 5, 6. 5. Yeah, 6.5. Somewhere around here. And that's a little bit too big, but yeah, sorry, somewhere around here. So that's going to be your y-intercept. No x-intercepts. Let's see we already did the asymptotes, we already did the domain, basically. We already did, the asymptotes, we did this stuff. So let's go ahead and basically find, the local maximum and local minimum. Let's go ahead and plot those things in. So we have the local maximum of -3.7 and then the y value is -0.46. So let's go to -3.7, -123.7, which is going to be somewhere around here. And the y value is -0.46, so it's gonna be somewhere over here. 1, 2, 3. Well, that's 1, 2, 3.7. Somewhere over here. That is going to be basically your local maximum. -3.7. -0.46. Let's go ahead and label that. Now that's going to be your max. Let's go ahead and do our local minimum, which is -0.26 and +6.46. So -0.26, so somewhere all the way over here, all the way to +0.46. Just going to be somewhere around here, somewhere around there. I'm not going to go ahead and, basically, let's just go ahead and label it -0.26 and then 6.46. All right, so that's basically how we do that. That's our minimum and maximum. So let's find out where it's increasing. It's increasing from -infinity all the way to 3.7. So -infinity all the way to 3.7. That's why it's increasing. It's going like this. It's increasing. So let's go ahead and draw that part in. So I'll be right back. I'm going to draw that part in. So I drew it in red. It's increasing, right? It's increasing. That is what our our increasing slash increasing and our decreasing interval is telling us. But where else is it increasing? At negative 2.6 all the way to infinity. So negative 2.6 right here, where we established all the way to infinity, positive infinity, right? That's where it's also increasing. Negative 2.6 all the way to positive infinity. Let's go ahead and draw that with the red pen. It's going to look something like that. Remember, do not let our line touch the asymptotes. Never let them touch the asymptotes. They can get super close, but don't ever let them touch. So we found our, let's go ahead and see where it's decreasing. It's decreasing from negative 3.7 all the way to negative 2. So negative 3.7 all the way to negative 2. But it's an asymptote, so it's not going to touch. So it's just going to decrease from negative 3.7 all the way to negative 2 and never touch the asymptote. So let's go ahead and draw our function, basically our line function decreasing. Let's go ahead and do that right now. So that's how it's gonna look like. So let's see what else this thing says. So it's decreasing from negative 2 all the way to negative 0.26. So our negative 2 is here, right? And it's gonna decrease. It's gonna go this way all the way to negative 0.26. That is what this thing's telling us. So let's go ahead and do that. So now that is what it's going to tell us. So it's going to look like that, decreasing, all right, and then increasing, increasing, and then decreasing. So now we're done with this part. Now let's go on to our concavity. So it goes concave up. Remember, it goes concave up like that, right? Like that, from negative 2 all the way to infinity. So it goes up from negative 2 all the way to infinity. It's going up. It's concaving up, right? So that is what that means. It's going up, concaving up from negative 2 all the way to positive infinity. And it's going down, concaving down like that, right? From negative infinity all the way to negative 2. Negative infinity, negative infinity all the way to negative 2, concaving downwards. So that's what that is telling us. No inflection point. So there's no inflection point because we use the asymptote. So there's no inflection point. Basically no point that tells us when the concavity switches. So that's basically it. That is how you graph this one curve from basically all the information that we have gathered here. That is how you graph it. Remember, just like this. No, just like that. No symmetry, no whatever. Asymptotes, concave up, concave down. So that is how you graph this one curve. All right, that's it.